Anyway, I'll give you some brief motivation and introduction, which will be followed by models for reliability and availability. And I will try to use some real examples. And I will also mention some challenges as I feel. And of course, the young people out there are much smarter than me, so they should be able to solve some of these challenges. So the motivation is very clear that today we depend on technical systems, computer communication and other systems for just about everything we do in our life. So we want them to be reliable and available. But we look around and we find even among very high-tech companies, there are lots and lots of failures out there that are documented and continue to do so. And there have been some major examples of failures that actually cause people's death, like the Boeing 737 MAX. So it is clear then that failures and downtime due to these failures lead to loss of reputation, like Boeing lost a reputation for a while, and maybe it still has due to that 737 problem. Loss of revenue, Boeing lost a lot of money as a result of that problem. And as we saw, possible loss of life. So these are serious problems. And so we need methods that, on the one hand, reduce failures of systems, as well as reduce the downtime caused by these failures, which may be contributed by hardware, software, or even human beings. But at the same time, we also need methods that allow us to assess the level of reliability or availability that the system has, and also find bottlenecks if you want to improve system reliability and availability. And these methods can be and have been used to compare design alternatives at the time of design, find bottlenecks to answer what-if questions, to optimize a design, to conduct trade-off studies between performance and reliability, or cost and reliability, and power and reliability, and so on. These methods have been used at certification time, at design verification testing time, even at the configuration selection phase, and not so much so far, but I would like to see more and more use of these methods, at least in the computer and communication setting, during the operational phase for system tuning and online control. So then we need to, this lecture is about these methods, rather methods of doing system reliability and availability assessment, not about the methods of reducing system failures and downtime. So what are the different methods in a very broad sense for quantitative assessment of reliability or availability? On the one hand, we have the data-driven approaches, which in this case will become failure or recovery data analytics in the modern terminology. You have collected data about the past failures or recovery from failures, and that data can be analyzed using statistical techniques to assess the reliability or availability of the system. An alternative to that is the model-driven approaches, and models can be solved analytically if you're lucky. Otherwise, you may use simulation, discrete event simulation, and many times, and I think I would like to see more and more in the future, combination of analytic and discrete event simulation in the same for the same system model. But what I find is that oftentimes people mistakenly believe that analytic methods are only applicable for simple models where you can find a closed form solution. Well, there are many large number of model types that may not be so easily solved by hand or in a closed form, but you can numerically solve the underlying equations, develop the equations automatically, and solve the equations numerically using a tool. So numerical solution of analytic models is not as well utilized as it could be, and therefore I find in practice unnecessarily excessive use of simulation where analytic techniques would have sufficed. And most of my life I've been trying to show this to people, both in academia as well as in practice, as to there are methods available, there are tools available, software packages available that will enable you to solve a large class of models analytically, numerically. And so we can say that the first approach, the data-driven approach, may be called the black box approach, where the measurement data is collected from real system, which is followed by statistical inference. Here, the system is treated as a monolithic whole without explicitly taking into account its internal structure. And this is clearly very expensive, especially for ultra reliable systems. Like, for example, Boeing 737, if you wanted enough data from which to then assess its reliability, it will take many years of data collection. So generally applicable, this method is generally applicable to small systems that are not very highly reliable. And furthermore, this method of data-based assessment of reliability is not feasible for system that is undergoing design or development. So the alternative, as we have talked about, is model-driven approach, which may also be called white box approach or gray box approach. So when no data is available for the system as a whole, which is the case when system is being designed, then we might use a probability model. And these probability models are many in this context: reliability block diagrams, fault trees, reliability graphs, Markov chains, semi-Markov processes, and so on. And these models will be constructed based on the known internal structure of the system and its components, their characteristics, that is component characteristics, and the interactions between these components. So we are then essentially deriving the behavior of the ensembles of that is combinations of components to form a system from first principles. First principles meaning probability theory. And these can be used to analyze a system with many interacting and interdependent components. But of course, in order to solve a probability model, you need input parameters for components and subsystems. And these input parameters will have to come from real data. So in effect, what we are talking about is a combined approach where we use a black box approach at subsystem or component level, and we use white box approach at the system level. And this is what we do in practice all the time. Thus, a combined data plus model driven approach is what is to be advocated in practice. So now most of the talk will be on this model driven approach, and a little bit at the end, if I get time, on data plus model driven approach. So model driven approach, most of the actual examples that I have done with real systems are they use this package that we have developed called SHARPE. SHARPE stands for Symbolic Hierarchical Automated Reliability and Performance Evaluator. And the first version was released in 1986. And of course, it has been continually improved, developed further, and so on. It's a stochastic modeling software package for model-driven assessment of reliability, availability, performance, performability, and so on. It has been installed. I don't keep a very strict count, but maybe about 1,000 sites, both companies and universities. And it has been ported to most architectures and operating systems. And it is used in teaching, it is used in research, and it is used in engineering practice. Some of the users company-wise, Boeing, EMC, AT&T, Alcatel, Lucent, IBM, NEC, Motorola, Siemens, GE, HP, Raytheon, and Honda in Japan. And this is the site from which people can download information about it. And it forms the core of Boeing's internal tool, which I helped them develop, called IRAP. Now, but I want to mention one thing. This is a quote that I've used a long time ago, that just having a tool doesn't solve all your problems. If you don't know how to model, or if your data is not good, input data is not good, then the answers will be as bad as anything. And so this quote is useful. A fool with a tool is still a fool. But there was a book that we wrote on SHARPE a while ago. This book needs to be, second edition needs to be developed because this is quite dated now with respect to the tool itself. But still, nevertheless, it is a useful reference for SHARPE. So now, if we are going to continue to talk about analytic methods, then I would like to divide the analytic methods into three broad categories. One group of methods I like to call non-state space methods. The second group of methods I like to call state space methods. And third group of methods I'd like to call multi-level model composition. So let's start very simply with the non-state space methods. And non-state space methods can be further classified into series parallel reliability block diagrams, fault trees without repeated nodes and with repeated nodes, and non-series parallel block diagrams, which are also called rel graph or reliability graphs. The main idea here is that although there is an underlying state space for each of these model types, we don't need to generate the state space. We don't need to store the state space. We don't need to solve the state space. We can solve the problem without generating the underlying state space. That's why I call them non-state space methods. And the reason for this ability is the key independence of assumptions that is often made to solve these models. And of course, all these models have been extended to multi-state component systems, phase mission systems, and so on. We'll not get into that. But so let me give you, and there are many examples of this that all of you know, perhaps. But I want to take one interesting example from real life that I came across of this last category of model type called reliability graph. There is some crosstalk. If there's a question, please ask. Otherwise, mute your microphone so there is no crosstalk, please. So this is a real world example from Boeing commercial airplane group. So each time a new plane is developed, reliability analysis of each major subsystem of that plane needs to be carried out by Boeing and presented to Federal Aviation Administration for certification. Now, most of the time, subsystems are improved versions of modified versions of subsystems in earlier planes. And therefore, models are also modified versions of the earlier models. Occasionally, there is a entirely new subsystem. So there was such a new subsystem in Boeing 787 when it was developed. And so for this subsystem, model needed to be done from scratch. And it so happens, so a particular subsystem in Boeing 787 that was entirely new is called current return network. And it turns out that several of my former students, PhD students that Professor Fong mentioned are in Boeing Reliability Engineering Group. So they were tasked with this analysis, and they called me and they said, we are going to do this, and it turns out that it can be cast as a reliability graph, as in SHARPE. So they said we are going to model this and we're going to solve it using SHARPE via IRAP. Remember, the Boeing tool is called IRAP, and SHARPE is at the basis of it. And I said, makes me very happy. Let me know what happens. So what is a reliability graph? It consists of a set of nodes and sort of edges. And edges represent components that can fail. And there is a source node and a target node. And system fails when there is no path from source to target. And we are asked to compute the probability of a path from source to target. And this problem is also known as ST connectedness problem or a network reliability problem. Fairly very well known problem. Current return network was modeled as the reliability graph, and I'm not sure this is exactly the picture, but something like this was the model of the current return network. And so such reliability graphs are very well known, and there are many well-known solution methods, and a couple of them are listed here. One method is find all the min paths from source to target, and after that you have to do the probability of the union, and this is often done using what is called sum of disjoint products. Alternative one is called BDD, binary decision diagram based methods. So both these are implemented in Sharp. So in a sense, this was a problem already solved in that sense. But Boeing tried to use Sharp for this problem, and it didn't work. Now, the reason it didn't work is quite clear, that the number of min paths is estimated in this problem to be 4.2 trillion. 4.2 trillion. Trillion is the number we often hear in terms of budget deficit in US, $1 trillion or something. This is number of min paths in this problem. So there is no way in the world any algorithm, any tool, anybody can generate these min paths and do the probability of the union. But the problem had to be solved in order for certification of the plane. So they asked me, my students, former students called me again and said it didn't work, and this is the reason, and what can we do? I said, I have an idea, and I have a very good student whom I can send you. So I sent this student, Daji Wang, for 4 months to Boeing, I think in 2007 or 2008, I forget. And the idea was extremely simple. Computing bounds instead of exact reliability. And if you take a subset of all the min paths, you get a lower bound on reliability. And if you get a subset of min cuts, you get an upper bound. And if these two bounds are close to each other, then you solve the problem. But actually implementing this idea in an efficient way took quite a while, but it was done within 4 months. And it turned out that the problem was solved within 900 seconds of computer time. These are upper bounds on unreliability, upper and lower bound on unreliability. That was computed in 900 seconds. So the problem was solved, and Boeing liked this algorithm so much that they decided to patent the algorithm. So algorithm was patented in 2011, and 2014 we managed to publish it in a European Journal of Operations Research. But let me now tell you something else practically that happens. So after this problem was solved, they took it to Boeing, to FAA, Federal Aviation Administration, and they said, fine, but now tell us what tool was used to do this computation. So they said they used Sharp via IRAP. They said, was Sharp developed using this DoD standard called DO-178B for developing software? So Boeing sends me a thick book, about 600 pages of this DO-178B standard, and asked me if Sharp was developed using this standard. I never heard of this standard before, and probably 50 different students and postdocs have programmed parts of Sharp. So it turned out that it seemed we had solved the problem, but not really. And so what I decided to do is dumped everything that was in my brain with respect to Sharp, any papers that we have published, any comparisons we have made, and I put together a document which I call Validation of Sharp. And I sent it to Boeing, who then sent it further to FAA. And lo and behold, for whatever reason, they accepted the document instead of DO-178B. So anyway, and now I'm told that this algorithm and Sharp are always used for any subsequent airplane that Boeing develops for CRN, that is current written network subsystem. So that gives you some idea of how practical problems are. So these non-state space methods that we have talked about so far are they involve things like reliability block diagrams, fault trees, and reliability graph. And they are easy to use and have relatively fast algorithms if you can assume that all components behave independently with respect to their failures and with respect to repair if repair is involved. And then there are many algorithms such as series parallel composition, factoring or conditioning algorithms, find all min paths or min cuts followed by sum of disjoint products, or binary decision diagrams, and lastly these upper and lower bounds that we developed for Boeing problem. But the problem is that dependence does occur quite often in practice with respect to failures and with respect to repairs. And these simple model types that we described are not easily able to handle these. And these kinds of dependencies, such as shared repair, warm or cold spares, imperfect coverage, state-dependent failure rates, non-zero switching time, non-zero travel time of repair person, reliability with repair, and so on. There are many situations that you can demonstrate that dependencies do occur, and we need to capture them in order to make our results meaningful. If you ignore these dependencies, your reliability and availability results you produce by your models may be way off. And so we need to move beyond these very simple non-state space methods to what have been called state space based methods. And Markov chains are probably the most important such method. So to model complex interactions between components, we need to use paradigms like Markov chains or more generally state space based methods. And many examples of dependencies among system components have been observed in practice and captured by continuous time Markov chains. In fact, what we are going to talk about are homogeneous continuous time Markov chains, or CTMCs, and the extensions of Markov to Markov reward models makes computation of measures of interest from simply probability vector relatively easy. And there have been many other books, but 3 of my books extensively deal with Markov chains. So let me give you a couple of examples of Markov chains, practical examples. So we are moving from non-state space methods to state space methods, such as continuous time Markov chains. And the couple of examples that I want to present to you, this was a model of Linux operating system we used at IBM for their Blade Center. So suppose that the operating system is up and running, and after some time it fails. Lambda OS is the failure rate of the operating system, and there may be a detection delay. Delta OS is the detection rate, and after the failure of the operating system is detected, you may reboot the operating system, and the reboot may be successful with probability BOS and not successful with probability 1 minus BOS. If reboot is not successful, you need to call somebody, this is the travel time, and patch the operating system. So this is a very simple example of a Markov model, homogeneous continuous time Markov chain, where the transitions are labeled with rates of transition rather than probabilities. Probabilities occur when we talk about discrete time Markov chain. Here we're talking about continuous time Markov chain. More interesting example we had developed for, again, IBM, when we were studying WebSphere application server, pair of them to improve reliability and availability. And this particular situation we discovered had multiple detection mechanisms and multiple recovery methods after software failures. And each stage of recovery had a delay and a possibility that that particular action will not succeed, so-called imperfect coverage. And so to capture all this, so failure detection could occur by what is called a workload manager, WLM, or by a node agent. And if both of them don't work in detecting the failure, then there may be manual detection. And after detection, if the detection was by workload manager, there'll be a failover to the identical replica. And if the failure was detected by node agent, then the WebSphere application server will have an automated process restart. And if that doesn't work, either one of these don't work, then there is a manual recovery by means of first process restart. If that doesn't work, then by node reboot. If that doesn't work, by actual repair. So all this was captured by this particular Markov chain. I want to also tell you in practice that software failures and recovery after software failures, very little information was available either in any document or in any one person's mind. I had to ask repeated question, loaded question like this. After a failure occurs of the app server, was there a detection? And then they will come back after a week of questioning each other. Yes, there is a detection. And I said, by what method? They will tell me WLM or node agent. I said, what if WLM doesn't detect and node agent doesn't detect? Then what? Then they told me after a week manual detection, and so on. So all this was developed. The model, the thing behind the model was not sitting there. I had to ask repeated loaded questions based on my prior experience, and that's how this model was derived. So discovering the recovery behavior of the system after a failure was actually the most important part of the exercise. So what we then have is a homogeneous continuous time Markov chain with a matrix which has this very nice name called Infinitesimal Generator matrix. So internally, a Markov chain is nothing but a matrix, and efficient and scalable algorithms are known for storing and solving such Markov chains. And steady state behavior essentially is solving this vector matrix equation. It's a linear system of equations. Only problem is that Q may have million by million or 10 million by 10 million. So we may not have 4 by 4, but pretty interesting size problems. Transient behavior is obtained by solving this Kolmogorov differential equation. This is the ordinary differential equation initial value problem. And once again, we know how to solve such models for tens of millions of states. Cumulative transient behavior, less known, can be obtained by solving this dl by dt equals LTQ plus pi 0, where LTs are integrals of state probability vector. And derivatives of these things can also be computed to find parametric sensitivity functions. Now, what am I doing with respect to time? Okay, I have half an hour, right? Okay. So what are the challenges in doing these kinds of models, Markov models? So modeling interdependence among components, we concluded simple non-state space methods don't work. RBD, fault tree, reliability graphs, etc. We need to use Markov chains and other state space methods. But the number of states of the Markov chain for any reasonable size problem would be so large as to preclude not just solving, but even generating the state space and storing the state space. In fact, the bottleneck seems to be largest bottleneck is generation of state space. Next bottleneck is storage of the state space. And the solution of the large state space is relatively trivial problem among these three. So state space explosion. The number of components in systems can be hundreds or thousands. And the number of states in a Markov model will be, as my grandson will tell you, gazillion states. Whatever gazillion means. Impossible to deal with. So what do we do? Well, state space explosion can be avoided by decomposing system into subsystems, modeling each subsystem separately, and then composing submodels results together. And we can use state space methods in those subsystems for where dependence is heavy, and use simple methods, non-state space methods, when dependence is either not there or very little. So we can combine, mix and match in these multi-level models. We can mix and match these different types of modeling paradigms. So what we have is a multi-level, multi-paradigm methods is what we use in practice in order to solve real problems. So let me then give you the second real problem that this talk has. In my books, there are many, the green book in particular with Bobbio has many such real world problems. But these are the two I'm most proud of, Boeing example that I gave you and this high availability SIP system for IBM that we did. So case study here is that IBM developed a high availability system for SIP. What is SIP? So this is a real world problem from IBM, and SIP stands for Session Initiation Protocol, which is what is used for voice over IP. And hardware platform that IBM used is the IBM Blade Center. The software platform IBM used was IBM WebSphere. And telco customer that IBM wanted to sell this system to heard the IBM's pitch on the architecture and all the other details. But they said that they need some numbers and they need some models that will generate these numbers in order for them to believe that this system will have the level of availability and reliability that IBM is claiming. So it turns out that, of course, IBM is a very large company, but the particular group of engineers that was dealing with this particular system, they did not know how to go about doing this model. But somebody told them that there is this fellow Trivedi at Duke who can probably help you. And so they approached me. They asked me to actually head this project, which is rare that an outside IBMer is a non-IBMer is asked to head a critical project within the company. So IBM asked me to lead the modeling project to quantify two things. One is system steady state availability, and the second was a user-oriented metric called DPM. It turns out that I'm only going to describe to you system steady state availability. I'm not going to describe to you the second part, which is also very, very interesting. So when I started this project, this is the picture they gave me. Analyze this, analyze this. You know, there is a famous movie with Robert De Niro, Analyze This. So this picture tells me several things. One is that there are two blade center. This is a blade center chassis, and this is a blade center chassis. So there are two blade center chassis, and each chassis has 4 blades, 1, 2, 3, and 4. 1, 2, 3, and 4. And apart from the operating system in each blade is a node or a blade, whatever you want to call it. And so each one of them has an operating system, which in this case is Linux. And one blade in each blade center is a SIP proxy server. So these are software, right? Software applications. And in the two app servers, WebSphere Application Server stands for AS. AS stands for WebSphere Application Server, or WAS. There are two app servers located in one blade. And so there are overall 6 app servers in one blade center chassis and 6 app servers in another blade center chassis. And 2 app servers in individual blade centers, they form a pair, which is called a replication domain. Okay, so given this information, first I concluded the following from that. Hardware configuration wise, the architecture used 2 blade center chassis, and they told me, and 4 blades each. And they told me that one chassis would have been enough from the performance point of view, that is how much load carrying point of view. But they used 2 chassis for fault tolerance or improving availability. Software configuration wise, there were 2 copies of SIP proxy as I showed you, and they told me one would have been enough for performance. So once again, they're using 2 for redundancy. And there are 12 copies of app servers, although 6 would have been enough for performance. So once again, they're using software redundancy. So they and each app server instance in one chassis forms a redundancy pair with corresponding app server instance in the other chassis called replication domain. So the system has both hardware redundancy and software redundancy, but the software redundancy of the type that is used here is very different from what you find in the literature. And I don't have time to get into that. It's a separate talk by itself. A very interesting idea of software redundancy. But today our concentration is on availability model. So then I started to ask them what components in the system can fail, both hardware and software. And there turned out to be 112 components. And these component failures can be divided into hardware side and the software side. On the hardware side, there is a power subsystem and its components within power subsystem can fail. There is a cooling subsystem and components within that can fail. Each blade has a memory subsystem, a network interface card, CPU, base, I/O, and a mid-plane network. It has networks, Ethernet and other networks. On the software side, each node is a Linux operating system, and the application-wise, some nodes have WebSphere application server, and some nodes as proxy server, as I showed you earlier. So after having gotten the information about each component that can fail, then I want to ask them about the recovery from that components. And before we go on, I would like to also mention that a single monolithic Markov model will have extraordinary number of states, at the minimum 2 to the 112, but a lot more than that. So we have to use something else. We use a multi-level approach. Subsystems are going to be modeled using Markov chains to capture dependence within the subsystem, and fault trees are going to be used at higher levels, as independence across subsystems can be reasonably be assumed. So this is an example of multi-level model composition. Single monolithic model is not constructed, stored, or solved. Each submodel is built and solved separately, and results are propagated up the higher level models. And our software package SHARPE, H stands for hierarchy, facilitates such multi-level model composition. So what we are now talking about is we have moved from earliest non-state space methods, which are efficient and simple, to state space methods, which capture dependency, to multi-level model composition to avoid largeness. And so in this, there are two books that extensively deal with this. The old SHARPE book and the more recent book with Bobbio has a extensive information on this multi-level model composition, as well as other two. So just to give you a brief idea, the top level the fault tree model for this particular SIP application server is the following. So remember that there are two proxies, right? So if both proxies are not accessible to the user, then system fails. So system fails since there is an OR gate here. If this input is 1, system fails. So this input is 1 when both proxies, that's why AND gate here, both proxies are not accessible. And what does it mean for a proxy to be accessible? Or proxy to have failed, more correctly. So either the proxy software fails, this node stands for proxy software, or the blade server on which this proxy is located fails, or the chassis common part like the midplane, power, and cooling of chassis 1 on which this blade server is located fails. Similarly for the proxy 2. So this gives you an idea why this particular part of the fault. Similarly, on this side, I have 12 application servers, and I'm instead of 7 out of 12, I'm using K out of 12 to make it more general. So if 7 fails, then of course system will fail. And then at the bottom, in the middle level, I have the chassis common. There is a midplane, there's a cooling subsystem and a power subsystem. Any of these fails, that chassis common fails. A blade server has a base, CPU subsystem, memory subsystem, RAID subsystem, operating system, and Ethernet and Ethernet ports and so on. And then at the lowest level, I develop Markov models of each individual subsystem. So midplane model is developed, cooling subsystem model is developed. All these models are developed by repeated listening and asking questions to the designers who know the system very well. So they are not, I don't go with my own idea. I just ask questions, I listen, and then form the model. And so I develop model for CPU subsystem, power domain model, base and memory, and RAID model, and operating system model I'd already shown you earlier. And the app server model, part of it I had shown you earlier. But what is important, and this was very important to the customer of IBM, that we went through and reflected all the gory details of the system behavior into these models. These are not some random, you just put together something without knowing what the heck is going on. So it's very, very important to very carefully listen to all the system design details and reflect most important ones into the models. And so this is a cartoon of the whole structure, the hierarchy of models. So this model is solved separately and passed on the results up the chain, etc. All this is possible all within the same single file within SHARPE. So now after having developed the model, next you have to solve the model in order to tell the customer what the level of availability of the system is. So then we need parameters. So I divided the parameters into 4 groups in this case. One is the hardware component failure rates or hardware component mean time to failures, software component failure rates, and then delays that occur in detection of failures, restart, reboot, or repair. And then each stage of detection, restart, reboot, etc. has a possibility that it may not succeed. And that is called imperfect coverage for each of the above recovery phases. So I asked IBM engineers who are working with me for all these input parameters. Now I found that in all companies I worked with, the hardware component failure rates are the easiest. Nobody has ever said they don't know that. They have numbers in some table somewhere. Most companies don't have any idea of the software component failure rate. Some exceptions, I would say, but in the IBM was no exception here, that they had no idea and we had to assume something. This can be experimented with. You can actually inject faults in the system and find out how long does it take to detect the failure, how long does it take to restart and reboot and so on. And so this was done. Some other lab in IBM had done these experiments to give us these numbers. Usually for imperfect coverages, people use 0.9 and then vary to find the effect on the outputs of these variations. So these parameters, as I said, can be obtained by hardware component failure rates based on field data. They always have some numbers, and detection, restart, reboot, delay, etc. can be obtained from testing. And for imperfect coverage, agreed upon assumption and variation of the parameters. And software component, this was the most critical. We assumed something based on what I felt was right. So uncertain parameters, such as what I described above, sensitivity is to be carried out with respect to those parameters. Anyway, so the parameters that we had for this particular situation are given here. These are not necessarily real parameters, but just to drive the models, to show you something. Real parameters IBM hides from you, obviously. And so these are all the input parameters for this model. And after running the model, we can compute the downtime of the system. The last row is the relevant one because K7 is what was to be used. And it also tells you the downtime due to different parts of the operating system contribution to the overall downtime, hardware contribution to overall downtime, proxy server contribution to overall downtime, app server contribution, and total downtime, and so on. And we can vary this K and find out, and we do all kinds of other sensitivity analysis. So to conclude this part, we developed a very comprehensive availability model in which hardware and software failures were considered, hardware and software failure detection delays were considered, software failover delays were considered, escalated levels of recovery as it is known in telecom is automated and manual restart, reboot and repair, imperfect coverage for all stages of the recovery. Many of the parameters collected from experiments, some obtained from tables, few of them assumed, detailed sensitivity analysis to find bottlenecks and to give feedback to designers. And the second part, which I didn't describe to you, is developed a new method for calculating what is called DPM, defects per million, which is how many calls will be dropped due to a failure. And this takes into account interaction between call flow and failure recovery, retry of messages, etc. And this has been, this is an old slide. This model has been published. And what is most exciting for me is that we were told that these two models that we developed were responsible for sale of the system by IBM to the telco customer. So now I can I know time is running out, but let me abstract what we did in this model IBM exercise is this. We had several submodels, and these submodels were communicating with each other. That is, after solving a submodel, for example, mid-plane model was solved, and answer, which is availability of mid-plane subsystem, was sent to the top-level fault tree as an input parameter. So this arc indicates one model computes something, and its output is given as input parameter to another model. So such graphs, we call them import graph. So multi-level models need such graphs. So multi-level model composition. First question is whether decomposition is done at the system level, which is what I like to see. It can be done at model level, at a higher level model level, or it can be done at matrix level. But this doesn't make sense because problem is that developing the state space and the underlying matrix itself is impossible for real life problems. So the decomposition should be done at the model level or system level. And then there are no known formalisms for expressing such multi-level models. We need to develop a meta-modeling language. And then what kinds of quantities to pass between submodels? There are many possibilities here. By doing this kind of decomposition, are we getting an exact answer or an approximate answer? It depends, and there are cases in which exact is possible, and there are cases in which approximation results. And if approximate, what are the bounding or estimation of errors of approximation? Now, I showed you an example of an import graph. If import graph has no cycles like in our specific SIP example, then this can be called a hierarchical composition. But if there are cycles in the graph, then you need to resort to what is called fixed point iteration. And so the multi-level models can be further divided into hierarchical composition or fixed point iteration. And you find these very separate chapters in my new book, Green Book. So hierarchical composition and fixed point iteration. Many more examples of such multi-level models can be found in this newest book, and of availability models, reliability models, performance or queuing models, performability models, which is combining queuing and failure and repair, survivability models, dynamic fault tree models in this Green Book. So since we are coming to an end, I would like to briefly mention the point that this state space explosion that we have talked about, but still the problem is that system reliability and availability models do not suffice. We need to move to service or user-oriented measures, such as the DPM that we mentioned. And one interesting starting point is the interval reliability concept introduced by Barlow and Hunter in 1961, which has been further developed in a paper that I wrote for Hong Farm's journal IJRQS, Modeling User Perceived Service Reliability Based on User Behavior Graph. This is a very rich paper in concepts, but very little explored by other people. So if somebody wants to take it up, somebody who is mathematically oriented, this paper should be followed up, and tremendous amount of material in there. And in fact, what we developed for IBM for DPM is a very small example of that. And the second part of IBM's model that I didn't describe here is in this paper in ISSRE 2010. And I will skip this one. So the last part, which I don't have any time for, but I will mention briefly anyway, data plus model-driven approach. So let me go back to the original idea. There are two types of uncertainty in these models. One type of uncertainty is called aleatory uncertainty, which is that randomness of event occurrences in the real system. And that is why we need a probability model to describe the dynamics of the system. And model-driven methods account for this aleatory uncertainty. Your Markov chains or semi-Markov process or reliability block diagram, etc., have the randomness that captures this real system randomness, which is called aleatory uncertainty. But there is second type of uncertainty, which is called epistemic uncertainty, which is introduced due to finite sample size due in estimating parameters to be input to the probability model. And data-driven methods account for epistemic uncertainty in that when they do the estimate, they give you not only point estimate, but confidence interval. Confidence interval is large if the finite sample size is small. Confidence interval is small if the sample size is large. But when we normally do the aleatory models, we forget about this confidence interval. So there is a need to propagate this confidence interval through the aleatory models, propagating epistemic uncertainty through the aleatory models. And there has been some work done that I'm not going to be able to describe, but we have applied this to many different examples, and including the IBM SIP example, where there are 63 input parameters. And by using these ideas of propagating the epistemic uncertainty through the aleatory model, we have managed to show the effect of the confidence interval on the input parameters on the confidence interval of the output, namely system availability. And so at this point, I would like to close and say that techniques and software packages are available for the construction and solution of reliability and availability models of real systems. System decomposition followed by a multi-level model composition is the typical approach. And the modeling has been used at many different companies by me and others, as put in the slide here. And the model types in use are non-state space models or state space models and hierarchical composition of fixed point iteration. Models solutions can be analytic closed form, analytic numeric, or simulative. And software packages, SHARPE or similar tools are used to construct and solve such models. Challenges, I mentioned some of them, but there are many more, such as relaxing the exponential assumption, combining performance and reliability and availability, further challenges of model parameterization, and software fault tolerance via environmental diversity, model validation verification, and modeling security, survivability, and resilience. So at this point, I will like to close by saying thank you for listening to me. Sorry, I didn't